Okay, then welcome to a new session of this Latin American seminar on set theory called Seminario Colombo-Mexicano de Teoría Conjuntos. And today we are happy to introduce you to an excellent human being, an excellent mathematician too. He is Professor Paul Szeptycki. He works at York University in Toronto, and his files of expertise is set-theoretic topology. Then, Professor Paul, thank you so much for accepting our invitation to give a talk in this seminar, and we can start with your conference. Thank you, Professor Paul.
Oh, thank you very much. I'm hoping everyone hears me okay. If you want, if it's better for me to put earphones in with the microphone, I can do that. But if people can hear me okay, I'm happy to do it without. So thank you, Julian, for the invitation. It's very nice of you to have me. It's nice to be giving this talk. I think I wish I could see everyone's face. I did see a lot of familiar names as people were coming in, so it's really quite nice to know that there's some familiar friends who are there, and hopefully some of those of you I don't know I can eventually meet in person. That would be very nice. All right, so I'm going to talk about something called Ramsey-theoretic, what I'm describing as a Ramsey-theoretic strengthening of sequential compactness. I should say that the initial work is joint work with Wiesław Kubisz at the Czech Academy of Sciences. I had a lovely few months of collaborations with him last year on my sabbatical. I visited Prague, and this is really the main thing we worked on. It seems to be there are a few students here in Toronto, some visiting who seem interested in the topic. So I have some also ongoing continuations of projects here that I'll talk about. I'm mainly going to talk about the paper I wrote with Wiesław. So those of you who've already looked at it, I apologize, probably not much new will be here, but I will give some updates about what some other people have been doing and some new directions and questions at the end. So I'll hopefully get to those in time. Okay, so the main notion that we're going to be looking at and strengthening is that of sequential compactness. And I think the definition is due to Fichet. In the early history of the study of compactness, and especially among generalizing for metric spaces, a number of different notions were explored, and probably one that's still of great interest to people nowadays even is sequential compactness. So a space is sequentially compact if every sequence, which I'll denote by a function from omega into x, has a convergent subsequence. So by here, a convergent subsequence, I just denote an infinite subset of omega, and the subsequence is given by f's restriction to that infinite set. So I didn't say this here, but a convergent sequence, of course, is this A, and it's expected that A is infinite. And of course, convergence, we know what that means, so I won't define it, but or I will. There's a point, and every neighborhood of the point contains all but finitely many elements of the form f of n as n ranges over A. Okay, so let me proceed. I don't know if it was Hausdorff who proved this. I think, according to Engelking, Hausdorff proved that every countably compact space is sequentially compact. Certainly, it would then follow that every compact metrizable space is sequentially compact. And really, the first step is looking at a generalization of this. So I can't remember what I said next on the slide. So, okay. So the generalization is in the direction of Ramsey's theorem. So let me just take a moment to remind you what Ramsey's theorem states. It's the higher dimensional pigeonhole principle. So if you have any function from the R element subsets of omega colored with n colors, Then there's an infinite set, which is homogeneous for the function. That is, all of the R element subsets of H all get the same color, fixed color I, for some I less than n. H is said to be homogeneous for the function. So it's not necessarily an obvious thing to consider. Oh, okay, and the notation is, of course, omega arrows, omega Rn. And the question, of course, is that I would consider is, what if instead of mapping into a finite set or a finite set of colors, one maps into a compact space? So in what sense can we assert that there's a homogeneous set for the function? Or if you think about the definition of sequential compactness is a statement about functions from omega into a space. So in what sense can we generalize the notion of a convergent subsequence for higher dimensional functions on higher dimensional subset structures on omega? And so that's what we're going to do. And so we first have a generalized notion of a convergent sequence. So if you do have some finite natural number, and you have some infinite subset of omega, and you have a function from that the R element subsets of that subset of omega into a space X, we want to say that that function converges to some point in X if the same thing you have for regular sequences, but defined intuitively in the appropriate manner. So every neighborhood of P, so if you have this point P, you look at any neighborhood. If you look at S, and if you throw a finite set away from S, and you look at what happens to all those R element subsets, they all get mapped inside the open set. So this is the point P, and this is some open set U. Okay. So it's just the same definition as for a convergent sequence, all but finitely many points in S their images lie inside of the open set. But here, of course, it's more complicated. We're looking at all the N element subsets of that, and all of those sets would get mapped in as well. All right. So, okay, this is not really important except to get a sense of the definitions, but let me just make a couple of trivial or obvious comments. If R equals 1, then this notion of a convergent sequence is the same as the usual notion for that we're all familiar with from basic topology or analysis. In the case of n equals 2, this notion was already studied by Knaust, who introduced it a notion of like a Fréchet type convergence notion, and he was interested in it. He's very interested in convergence properties of Rosenthal compacta. And he studied this notion of convergence in the case n equals 2. Among other things, he proved that every Rosenthal compact has a natural convergence property. It's a two-dimensional convergence property similar to the Fréchet-Urysohn property. I won't define it, but I can give the references if you're interested. And just a trivial observation: if you do have so what does this have to do with if we have lots of convergent sequences in the classical sense, what can you say about the existence of convergent sequences in this higher structured sense? Well, if you have some convergent sequence to a point P in a topological space, and if you define the function f on omega to some finite size r, so all the R element subsets on omega, just by letting f of s be the x which is indexed by the minimum element of s, then this function, it's an easy, just check for yourself, this function converges to P in this new sense of this new higher dimensional sense. And one other thing, if you just want to get some feel for the topic or for this new notion, if you do have a convergent sequence in this sense of in this definition, and you just take any pairwise disjoint collection, I guess this is inside of S to the R, of course. And if these SIs are pairwise disjoint, then if you just look at the images of those F of SIs as a classical sequence, then that also converges to the point P. So I don't think these last two observations are anything we'll use or rely on, but I think it's just helpful if you have not seen this this definition before, to give yourself a little intuition about how it what it means. Okay, so so now we want to define a strengthening of sequential compactness, which I think we're in the middle of renaming, but when I wrote the paper with when I was discussing this with Yeswa, we decided to call it Ramsey spaces or R Ramsey spaces. Now that's not a great notation because that's already used, I think, in to mean something else in other contexts. I mean, related, but Ramsey-theoretic, but not exactly this. We have some other ideas about what to call it, maybe N sequential compactness. But so given given an integer R in a topological space X, we'll say X is R Ramsey if essentially any sequence has a convergent subsequence. So, but any R dimensional sequence in X, there is an infinite subset, so that the subsequence F restricted to the R element subsets of S converges. And we'll say that X has the Ramsey property if it's R Ramsey for all finite R. Okay. So a couple of more, a couple of simple observations about this. The first one is that one Ramsey is just the statement that X is sequentially compact. Every sequence has a convergent subsequence in the classical sense of the sequence. And it's also fairly easy to show that if you are R plus one Ramsey, then you're R Ramsey. And the idea is, if I have, of course, some function from the R element subsets into my space X, I can soup this up to a function from the R plus one element sets by declaring F at S is, I guess you throw away the top element, is equal to F at S minus the maximum. And then if you know your R plus one Ramsey, a convergent sequence for capital F will give you a convergent subsequence for little f. So this is just nothing deep or complicated here, just straightforward. A couple of other comments. Oh yeah, so Ramsey's theorem just can be restated as every finite, well, usually you think of a finite discrete space, but the separation axioms aren't necessary here, but every finite space has the Ramsey property. So if you map into a finite discrete space, the only chance of having a convergent sequence is if you're constant. And so this formulation of this notion of Ramsey's theorem is can be restated in this topological way. Oops, is that what else thing I want to say here? I thought I wanted to say something else, but I guess not. Okay, so the first result is a natural one, that if you're compact and metrizable, then you have the Ramsey property. So you are not only, we know that compact metrizable spaces are sequentially compact. So this is a strengthening of that result by saying compact metrizable spaces have the Ramsey property. I'll give a sketch or a proof in a second, but let me make some more comments about it before I give the very quick proof. Some observations. So of course, this theorem, just by as what we observed, if we apply the theorem to a finite X with a discrete topology, that's a compact metric space. That's Ramsey, and so Ramsey's theorem actually follows from this theorem. This theorem in the case when R equals 1 is just the classical theorem that compact metrizable spaces are sequentially compact. So it's a generalization of that. And finally, all of this work was inspired by a very small short paper, 2 or 3 pages long, by Bojanczyk, Kopczynski, and Torunczyk. And they proved this theorem just in the case of R equals 2. And they were interested in some applications. So they used it to, they applied it to show that they can obtain idempotence in compact metrizable semigroups as limits of some particular functions on the 2-element subsets of omega. So anyway, this is one of my maybe not very well formulated questions. I mean, not precise, but I really do think there must be some other algebraic applications of this notion of the stronger notion of sequential compactness, maybe similar to what's proven here, but we really don't have any applications so far. The only applications we have is, just I find this to be a very nice property. There seem to be some very combinatorially difficult problems that are fun to work on, and it seems very interesting for its own sake. But I do believe there should be some interesting applications that we haven't found yet. All right. So, how do you prove this? It's actually, pretty straightforward. So you want to prove that a compact metric space is R Ramsey. So you take your function from the R element subsets of omega into my space X. And then you cover the space by finitely many open sets of radius 1/2. So all of these have radius 1/2. And then you find one of those, and you find maybe S0, and F at S0 squared is entirely inside of, maybe this is U0, that has diameter 1/2. And then you take a finite cover by open sets of diameter 1/4. And so forth. And inside U0, you find one of them, and you find S1. So F of S1 squared is inside of U1, and the diameter of U1, I guess if the radius 1/4, the diameter of U1 is less than 1/2, and the diameter of U0 is less than 1. Sorry, I had bad notation, but my handwriting is terrible, but the diameter of U0 is less than 1, the diameter of U1 is less than 1/2, and we're building this decreasing sequence of sets. So I have this written out after I go to the next slide. So for each n, you fix an open cover by 1/2 to the n balls. So I guess one thing I didn't say very clearly, but this induces a finite coloring of omega to the R. You ask which, if you have an R element subset, you ask which of the finite open sets is omega to the, is the image of omega to the R contained in, and then that gives you a finite coloring of omega to the. So you have a finite coloring, and so you can use Ramsey's theorem for each of these and build recursively a decreasing sequence of infinite sets, where the diameter of the image of each of them is less than 1/2 to the n. And then if you take the point, which has to be the unique point in the intersection of their closures, and you take any pseudo intersection of the sequence of the SNs, then that's easy then to show that that gives you a convergent subsequence convergent to P. Okay, so I went over that maybe a little bit quickly for some who maybe is not familiar. Are there any questions about that proof? Is there anything I can try to clarify if it's not clear? Okay, I think it is pretty straightforward. It's the same proof that one uses to prove that compact metric space is sequentially compact. One does the same thing and builds the infinite decreasing sequence and takes a pseudo intersection, and one gets a convergent sequence in the same way. So it's the same proof, nothing really new here. Okay. So a couple of things more that we can say though, other than just so let me say a few more. Let me say some things about more general things about spaces beyond metric spaces or metrizable spaces that have the Ramsey property. I won't give a proof of this one, but it's not really that surprising. But if you have a sequentially compact space, and if it has character less than B, which is the bounding number in omega to the omega, the eventual in the order of eventual dominance, then that's any sequentially compact space of small character has the Ramsey property. So for example, a first countable compact space has the Ramsey property. So first countable plus compact implies the Ramsey property. And we have other corollaries. So for example, one way of stating this to obtain some applications, if X is compact and the closure of every countable set is first countable, then X has the Ramsey property. Of course, we only care about the closures of countable sets because if you're looking for a convergent sequence, you're looking at omega to the R into X. So you just have to look at the image of all of those of the range of the function f and take its closure, that's a closure of a countable set. So if that's first countable, then you just work inside that first countable compact space and find your convergent sequence by the previous theorem. Okay, so that's the first was corollary. And then, so for example, if you take 1 point compactification of a discrete space, so no matter how big the discrete space is, if you take the 1 point compactification, then it has this property. If I take a countable set and take its closure, it just looks like omega plus 1 in the subspace topology. And so that's first countable, and so it has the Ramsey property. Another corollary, coarse and compact. Coarse and compact, of course, is a compact subspace of a sigma product. And if you're in the sigma product, and if you take countably many points, then the union of the supports of all those points is countable. And so if you take the closure, then the closure of that is first countable because the topology is completely then determined by the coordinates of the support of all the points in the original countable set. So coarse and compact have the Ramsey property. Coarse and compact have the property and the corollary, and so therefore have the Ramsey property. I'll mention one more result, which doesn't follow from this theorem, but it's independent of it. Sorry, one more. Compact linearly ordered spaces therefore have the Ramsey property by the same argument. And then another theorem, I'll say more about this theorem later because actually something a bit stronger is proven, which is I think of separate interest. But bisequential compact spaces have the Ramsey property. I won't talk about bisequential today, but the main point of this is that Rosenthal compact are known to be bisequential. So it's a weakening of first countability. And therefore Rosenthal compact or Ramsey, which is I think of some interest because sequential properties of Rosenthal compact have really been studied and considered by many people, and so this is a nice generalization. I'm more interested in this result because when we were talking to Stevo about this property, he really pointed us in the right direction as to what to consider next, and I'll talk about that at the end of the talk. Okay, so there are some counterexamples, or some examples. So first thing, of course, one can ask, the natural questions are, is this Ramsey property really stronger than sequential compactness? Are all these N-Ramsey properties different? It turns out that looking for counterexamples, looking at size spaces or Isbell and Rufka spaces is really the right place to look. So I'll quickly just remind people who may not know what an Isbell and Rufka space is. So first of all, almost disjoint. So two sets are almost disjoint if their intersection is finite. So if you have a collection of subsets of natural numbers that are almost disjoint, one can form a space which has as omega a bunch of isolated points. And then the other points of the space is the actual almost disjoint family A. So each of the elements of A correspond to a point in the space. And the neighborhood of the point A is, you look at A down below and you throw away some initial segment of A. And that's a neighborhood of the point A. And the fact that A is an almost disjoint family tells us that this is a Hausdorff space. So this is always, the space is always Hausdorff. Okay. And just by the definition, it's locally compact, right? Because each point has a neighborhood which looks like just a convergent sequence. And of course, that's a compact set. So it's locally compact in Hausdorff. So one can form its one-point compactification. So you have a point at infinity, and it's the one-point compactification of the space. So that's the space which we use notation K of A. Now, these kind of size spaces are really useful sources of counterexamples. I think if you take a maximal almost disjoint family, then before you take the one-point compactification, of course, just without the one-point compactification, it's already a pseudo-compact space that's not countably compact. So I think for many people, that's one of the main important examples. But there are lots of other things that they can be used to construct. So, for example, we'll talk about it right now. So if you take a maximal almost disjoint family, so maximal in the sense that every other infinite subset of omega has infinite intersection with some set that's already in the family A, so you can't extend it to a larger almost disjoint family, then the space K of A is not too Ramsey, but it is sequentially compact. I'm sorry, I should have mentioned that. It is sequentially compact. All right, so why is this? So I wanted to give a little short proof of this fact. So the sequential compactness, this is well known. If you have not seen this before, it would behoove you to take a moment and try to prove for yourself that the space is always sequentially compact. But let's just check that it's not too Ramsey, but let's talk about it more in general. So we want to say that this space will be R Ramsey. Any space of this form will be R Ramsey if and only if it's R Ramsey with respect to functions that go into omega. So why is that? Well, remember what our space looks like. It looks like omega. Then we have the set A, and then we have the point at infinity. Okay, so if we have a function that goes from omega to the R into the whole space, so if it's going first just into the whole space, there are three pieces to the space. So by Ramsey's theorem, there's an infinite set, so that restricted to the infinite set, f of s to the r is either entirely inside A, it gets mapped all to infinity, or in the case that we're trying to argue here, it gets mapped inside of omega. So we can forget about omega because we're trying to argue that that's the interesting instance, what happens for r-dimensional sequences that always get mapped into the isolated points omega. Well, if you get mapped into A, remember, then our space, we're living inside the compact space, which is just the one-point compactification of a discrete space, right? Because in the size space, this A is closed discrete. And so if I look at the one-point compactification of the whole space, A union infinity is just the one-point compactification of a discrete space. And we've already seen that that is, that space is Ramsey, and so we could find a convergent sequence. Okay. So in fact, yes, the only interesting case is what happens when we get mapped into omega. So if it's true that any function mapped into omega, you can find a convergent sequence, then the space has to be R Ramsey. Okay. And so then we have a couple of cases. If we have a convergent sequence, it converges to one of two places. It either converges to a point in the almost disjoint family. And for that to happen, you would have to have the whole of S minus some finite set, its R element subsets mapped entirely inside the set corresponding to that point in A. And so that's what it means to converge to A. Otherwise, if it's going to converge to infinity, the other possible place it could non-trivially converge, then you have to have that any neighborhood of infinity would contain the image of S minus n to the R for some n. So why is that? Well, if you think for a moment about the space again, let me try to draw it over here. We have omega, we have A, and we have the point at infinity. What does a neighborhood of a point at infinity look like? Well, it has to be the complement of a compact set. And what does a compact set look like? Well, any one of the neighborhoods of these points, along with their sets A, are compact sets. So a typical neighborhood of infinity is formed by just taking finitely many points from the closed discrete set A and a neighborhood of them, which means the set A, and throwing that away. And then what's left is a typical open set around infinity. All right, so that means that for any one of these A's that appears here, I have to throw away, if I'm going to have that the image of S minus n to the R is inside that open set, I'm going to have to avoid finitely many A's. But if I can avoid one A, if I can find an n that avoids one A, then taking a large enough n, I can avoid finitely many. Okay, so so this is what it means for a set to converge to infinity. So that means that every A can be avoided. Okay, so let's show that a mad family. So again, what I'm trying to prove is that if A is maximal, then Ka is not 2 Ramsey. Okay, so we need to give a function which witnesses the failure of the 2 Ramsey property. Okay, so we put A on omega cross omega to the Aleph 0, and really without loss of generality, we can assume that the columns singleton n cross omega are all elements of my almost disjoint family. The reason we can do this is if you have a maximal almost disjoint family, just take countably many of them. By throwing away finitely many points from each, you can make them disjoint, and you can make them cover the countable set on which the almost disjoint family is living. And so they look like the columns of omega cross omega. And then we define a function into the space by saying the two element set Kn will just go to the ordered tuple Kn in omega cross omega where K is less than n. Okay, and we want to show that this can't converge if A is maximal. So let's take any infinite subset and notice that if I look at the ideal generated by the almost disjoint family, the image of S minus n, so let me just draw a picture again of what this looks. We have omega cross omega. And if I look at some set S minus n, what we do is the image of that is just the columns above S with coordinates in S, above the diagonal, but past n. So I throw away n as well from each of these. So it lies in those columns. So what that means is right away it says that it intersects infinitely many elements of the almost disjoint family. And that's so the ideal generated by the almost disjoint family, so they're not in the ideal generated by the almost disjoint family, and that's referred to as the sets I plus. So they're large. So the image of any one of these things is large. And then of course there's a classic theorem, result of Matthias that says if you have a mad family and if you have a sequence of large sets, a decreasing sequence of large sets, then there's a pseudo intersection, which is also large. And of course, being large means that you have infinite intersection with many elements of the almost disjoint family. So that means if I look at any S, any infinite S, there is an element of the almost disjoint family that has infinite intersection with some pseudo intersection of this sequence of, so I guess, I'm sorry, this whole thing you can call Bn. So these Bn's are all large. And so there is an infinite subset of that, a pseudo intersection of that, which has infinite intersection with some element in the almost disjoint family, not just one, but many. So therefore you can't avoid that A. And so it can't possibly converge. Okay, so that's really the proof. All right, so I have about 20 minutes left. So I think that's plenty of time to say what I want to say. So let's just, I have to remind myself what I want to say. Okay. Okay. So how about an R Ramsey, not R plus 1 Ramsey? So once again, the whole point of the previous construction was this K of A, if A is a maximal almost disjoint family, is a sequentially compact space. So that's 1 Ramsey, but it's not 2 Ramsey. So we can distinguish sequential compactness from the 2-dimensional version of sequential compactness. But with a little bit more work, not yet in ZFC, but hopefully that's one of the questions. One can construct an R Ramsey K of A, which is not R plus 1 Ramsey. Now, of course, this almost disjoint family, if it's going to be R Ramsey, then of course A is not maximal. Right, because if it's maximal, it can't even be 2 Ramsey. So we're interested in R bigger than or equal to 2 and constructing an example. So let me just quickly sketch the proof to illustrate what's of interest in the construction and what might be of interest if you want to construct a ZFC example. Okay, so we're going to try to do the same thing that we did in constructing, in showing that a mad family is not 2 Ramsey. In that case, of course, we looked at omega cross omega, and we had a natural function which sent f of Kn to the tuple Kn. So we'll do the same thing. So we're going to build our almost disjoint family on omega to the R plus 1, and we'll use a similar function like this, or analogous function exactly, that will witness that will have no convergent subsequence to witness then that the space is not R plus 1 Ramsey. Okay, so and we do this, the setup is very similar. So we're going to build an almost disjoint family on omega to the r plus 1, and we'll start off by looking at all of the columns, essentially, of if you think of the hyperplane omega to the r, and you look at each column above omega to the r, that will be one element in my almost disjoint family. That'll be the initial partition of the underlying set into countably many infinite sets. Each of them will be in my almost disjoint family. As I said a second ago, so the not r plus 1 Ramsey will be witnessed by this function g, which takes a r plus 1 tuple, r plus 1 element set, arranges it in increasing order, and puts it inside of omega to the r plus 1 in increasing order. So it's sitting above the hyperdiagonal or whatever that's called in the space. And then we want to make sure that it's not r plus 1 Ramsey. So we're going to enumerate all infinite subsets of omega. And we're going to make sure that G restricted to B alpha to the r plus 1 can't converge. And it will be done in the same way. It'll be done the same way by finding an element of the almost disjoint family which cannot be avoided by throwing away initial segment of B alpha and looking at the image. And then, of course, we want to make sure that we are R Ramsey, so we need to enumerate all of the functions from omega to the R into, of course, as we already observed, if you're going to be R Ramsey, you only care about functions that map into the isolated points. So we can just restrict our attention to those functions which map into the isolated points, which is the set on which the almost disjoint family is being built. Okay, so I want to go down. Okay, so how do we make this construction work? So let me add an extra page here just to say something here. Okay, that's one. What do we need to do to make this construction work? Okay, so we need to fix, for each alpha, we're going to have to fix an S of alpha, which is convergent for F of alpha. So at some stage alpha, we have all of these, for beta less than alpha, we have all of these F betas of S alphas, and these are all supposed to converge to infinity. Restricted to F, to the R. They're all supposed to converge to infinity. How do we make sure they converge to infinity? We need to make sure that if I look at any alpha bigger than beta, A alpha has to avoid S alpha. So A alpha should have, we should be able to take A alpha, intersect it with this F of, let's say, S alpha, maybe minus N if you want, but to the R, this should be finite. Right? We want to make sure that's finite. So in some sense, these sets here, which we're interested in, we want to keep them small so that we can continue to avoid them when we add new elements to my almost disjoint family. But on the other hand, we want to make sure that we can at the same time, at some stage alpha, add a new element to the almost disjoint family, A alpha, which has infinite intersection with all G restricted to B alpha minus N to the R plus 1. So we also want to make sure that A alpha intersects all of these sets, G restricted to B alpha minus N to the R plus 1, that these are all infinite, but if it's true for all N, then not empty is enough. All right, so we want these sets to be small, maybe in some ideal is what we really mean, and we want this guy to be large. What I mean by small and large, of course, is I want some ideal And I want always that these sets, G restricted to these B alphas, to be large with respect to the ideal. But at the same time, we want all of these sets, F alpha, S alpha to the, this is R plus 1 here, to the R to be small with respect to this ideal. Okay, without going into the details, then as you're proceeding, if we're small, we can find another element. We can take the next element to the almost disjoint family and make sure that they are almost disjoint, not just from the previous elements of the almost disjoint family, but also from these sets of this form here, sets in the ideal. So really, we want some ideal so that the elements of the almost disjoint family are in the ideal. And so that if I have any countable collection of sets from the ideal, I can find something else which avoids them, and in the sense of being almost disjoint from them, but hits, that is, has large intersection with a large set, which is, of course, the sets of the form G restricted to B alpha to the R plus 1. So we're looking for a nice ideal, and that's exactly I'll just describe what the ideal is and the lemma that makes this all work. And the ideal is essentially the Fubini product of the finite ideal. So phin is the ideal of finite subsets of omega. And the Fubini product of phin is defined recursively by something is in the n plus 1 dimensional product of phin if the set of S in omega to the n, right, is in phin n, but the set of S's that satisfy something, so that the set of K's where S is extended by K is not finite, is indices which have to be in the finite set. So if most of the elements most of these sets are finite, but if they're not finite, the set of S's for which it's not finite is in the phin n ideal. Okay, so this is just the Fubini n-fold Fubini product of the finite ideal. And if you remember from the start, the sets we started with in the almost disjoint family were, we took an S in omega to the R and just took the column. So there's only one column which is infinite. So then we know that the ANs are in phin R plus 1. If you take something which is almost disjoint from all of these ANs, so if you're building an almost disjoint family and you start with these ANs, then it has to be almost disjoint it has to have finite intersection with each column. So we get right away that any set which is almost disjoint from all of these is in phin R plus 1. So as long as we build an almost disjoint family this way, this seems to be an ideal which might work. But then the main lemma we need, of course, if you look, of course, at the image of any infinite set under this function G, which we fixed, it's not in phin R plus 1. There are too many columns which fail to be in phin, so that's okay. And the last lemma, which is the key one that makes the whole thing work, is if I have any function from one dimension below, so omega to the R element set of omega into omega R plus 1, then I can find an infinite set whose image is in phin R plus 1. So it is in the ideal. So this phin R plus 1 is exactly the ideal we need to make the construction work. Okay, I'm not going to give any more details about it, but that hopefully gives a flavor of the construction. So the result is that under CH, the conclusion that's mentioned here holds, but I think the nicer results so far, and I think all three of these, Cesar, Carlos, and Osvaldo have much nicer results. They have an n Ramsey and not n plus 1 Ramsey from a variety of different assumptions. From just B equals C, which is, I think, just essentially the same construction, just remembering that character less than B is Ramsey, and so the construction go through, and some analysis of the cardinal invariance of the Finn ideal. But it's essentially the same idea. But some new ideas under B equals S, they also have an example. They also have the set, they can make the construction work. Or under the parameterized diamond B, and the dominating number is omega 1. So any one of those assumptions by themselves will give an example of an n Ramsey, not n plus 1 Ramsey. And I think I know from talking to a couple of these people that they have some enthusiasm and hope of getting a ZFC example, although that would be great, of course. So we'll see. They also very recently have shown that that there's a sequentially compact, not 2 Ramsey space of character B. That's a ZFC result. So that's nice because that shows that the minimum character of a compact, not 2 Ramsey space is exactly B, right? Because if the character is less than B, of course it is 2 Ramsey, and this counterexample gives an example, shows that's shown. Okay, so those are I think some nice results, new results in this direction. Yeah, so B is the minimal character of a sequentially compact, not 2 Ramsey, or even compact, not 2 Ramsey. Okay, so first instance of an interesting question: is there a 2 Ramsey, not 3 Ramsey space in ZFC, or n Ramsey, not n plus 1 Ramsey? So this question I think is still open. It's probably the nicest of the questions arising from this. And then I have a little bit of time, so let me make some comments about preservations under some operations, because there's one I think still interesting question there. And then if I have time, I'll say something else. But let's see. So the R-Ramsey property is preserved under closed subspaces, sort of obvious things, continuous images and countable products and sigma products. Maybe countable products is a bit, I can say something in a moment, but something more is known than countable products, which I'll state in a second. So let me mention some of these cardinal invariants that were looked at for sequential compactness and asked what are the corresponding cardinals for the Ramsey property. So Van Douwen showed that the minimal cardinal kappa, such that 2 to the kappa is not sequentially compact, is the splitting number S. So if you look at 2 to the omega, of course that's the Cantor set, metrizable, compact. So it is sequentially compact. And one can ask for what values of kappa, what cardinals kappa is 2 to the kappa sequentially compact. And if you go up to S, the splitting number, one can then build a sequence in 2 to the splitting number using the notion of splitting in the splitting family that has no convergent subsequence. And then also prove that any kappa less than that, it is sequentially compact. And what is S? Okay, it's the minimal cardinality of a family of 2 to the omega, which is splitting. It means that if you take any infinite set, F restricted to A is constant mod finite for all F in A. That doesn't happen for any A. So it is this is just a translation of the classical notion of the splitting family into functions. So it's the minimal cardinality of a family of functions. So if you take any A, there's going to be one of the functions inside the family on which also, what do I mean? This is what I mean. I'm sorry, I'm getting myself confused. Let me just leave it like that. But so one could ask, what is the cardinal for the Ramsey property? Okay, so there's a cardinal which was, I don't think was introduced by Blas, but I learned of it from Blas. Maybe it is due to Blas. It's in his beautiful article on survey on cardinal invariance of the continuum. But you know what it means for a set, if you have a function from R element subsets of omega into and you color them into 2 colors, what we mean to have a homogeneous set. But the question is, let's suppose you have more than one function. Let's suppose you have a family of functions F, and you have each one of them is a coloring of the R element subsets of omega into two colors. Can you find a single set A, which is essentially a homogeneous set for all of them? Mod finite, of course. So a set A is almost homogeneous for some family of functions if by throwing away a finite set from A, it will be homogeneous for a particular function in the family. So for every family F, throw away finite sets and you have a homogeneous set for F. And par 2 or par R is the minimal cardinality of a family of functions from two coloring from omega R into 2 with no almost homogeneous set. Okay, so a few things he proved about it is that these par R is of the same for all R. It's all equal to par 2, and it's the minimum of the cardinals B and S. And in fact, we can prove that par 2 is the minimal cardinal kappa, so that 2 to the kappa is not R Ramsey. And it's just really the same proof as for sequential compactness, but you look at what you need in the case of higher dimensions, and it's exactly this par function. So really par is exactly like the splitting number, but for higher dimension finite powers of R, or power sets of R. And it's known, but Schlott proved it's consistent that B is less than S. So if that's the case, then 2 to the B is sequentially compact, but it's not 2 Ramsey. All right, so that's at least a consistency is all about 2 to the B. So I'm out of time now, so let me just mention a question, because of course, another natural question is the productivity number. Like what's the minimal size of a family of sequentially compact spaces whose product is not sequentially compact? That turns out Simon proved that that's H. It's possible that that's H for the Ramsey property, even for the 2 Ramsey spaces, but I suspect there's some partition-like variant of H which might characterize it, and maybe it's different from H, but we don't know. So the question is, are there H many 2 Ramsey spaces whose product is not 2 Ramsey? If so, that would say that H is the productivity number for the 2 Ramsey property. Why is it bigger than or equal to H? Well, essentially the same proof that a product of fewer than H many sequentially compact spaces is sequentially compact. That same proof will generalize to the R Ramsey without really any changes. But whether or not there's actually an example witnessing that H is the exact productivity number, we don't know. So there's another question which I wanted to mention. And I'm out of time, but let me just say something about the further directions. You can, the point is that, Ramsey's theorem is just one of many Ramsey-theoretic type theorems. So, you could look for a family of subsets of finite subsets of omega. It has the Ramsey property. Whenever you partition it, there's an infinite set, so that when you restrict B to that infinite set, you're inside one of those colors. And so if you have any kind of family of sets with the Ramsey property, then you can have a notion of sequential compactness for that family of sets. So if you have a collection of finite subsets of omega, then and if you have a compact metrizable space, then and B has the Ramsey property, then you have a notion of B sequential compactness, and that compact metric space would satisfy it. And then one could study what these are. And for example, that result I mentioned earlier by Todorcevich, that compact bisequential spaces are Ramsey, he really proved stronger result that they're B sequentially compact for any barrier on, if you know what those are, on omega less than omega. And it was Nash-Williams who proved that barriers have the Ramsey property. So general problem is study and classify analogous notions of sequential compactness arising from different Ramsey families. And I know I talked with Julian, who invited me to give this talk, and he was suggesting some particular example to look at that I think is interesting and worth pursuing as well. So in terms of barriers, I have a graduate student here at York who is now working on that, and we have certainly outlines of proofs about distinguishing barrier sequential compactness for different types of barriers that I think are interesting, and hopefully we'll have something written up soon and can send it around once that's done. Okay, thank you very much. That's all. Oh, I think I have a last slide. Yes, muchas gracias por su atención. Thank you very much. Is anyone still there?
Oh, yeah. Thank you, Paul, for your talk, for your online. So we can few minutes for a question. Yeah, Luis. David, do you have a question?
Hi, Luis. I think you're muted. Okay, go ahead. Yeah.
Yes, I'm here. So first of all, sorry for interrupting with my lovely eyes. I was
oh no, that's okay. I appreciate that. I knew you were interested in those things, so I appreciated.
Oh, thank you. Well,
we're getting a reaction from the audience. Normally, you would see somebody's face light up with a smile, but so that
yeah, that would be my face. So first of all, well, thank you very much for the talk. I keep asking these guys to explain to me and the Ramsey property, and they never have time for me, and they always
okay.
So I'm sure your presentation was way better than theirs. So thank you very much for everything. So I have two questions. The first one is, you mentioned way at the beginning sequential property that the friend you have in Czech Republic found out about Rosenthal compactons. It was, I think, the second or third slide.
Yeah, the very first slide. So let me, I don't know if I can go quickly back to the beginning. No, there's a paper by those three Polish mathematicians who are interested in compact semigroups. And one of the, if you know anything about the work of Hindman, Hindman's theorem was a proof that about the existence of, if you partition the natural numbers into finitely many pieces, one of the pieces has arithmetic sequences of arbitrarily long length. And the tools that were used for this was the existence of idempotence in compact semigroups. So this idea of idempotent, that is a point in the semigroup where p times p equals p, I think is very interesting combinatorially. And what they were, for some reason, I don't know, there's not much motivation in the paper other than the statement and the proof. That is the statement that compact semigroup would have this 2 Ramsey property. And from the 2 Ramsey property, they construct an idempotence as limits of sequences of an aptly chosen function from omega, the 2 element subsets of omega into the space. So that was that was the original motivation, was that paper, and the realization that they only do it for n equals 2. There must be more going on here. Let's study this and see what we can find.
Okay, thank you. And the second one was about Todorcevic's results on Rosenthal compacton. Do you know if it's written anywhere or where I can?
I have a handwritten note. I'll be happy to share it with you. So that's fine.
That'll be great. That's everything. Thank you very much.
Thank you, David. Does anyone else have a question for our speaker? No.
I ask more questions if no one else wants.
Please,
So Paul is here, so I don't want to use all his time. But so I've been asking, you've thought a lot about these F-affine properties. Do you know any relation between these? Because I remember sometimes you said that they seem to be a little bit different. The N-Ramsey property.
Which properties?
The F-affine properties, or the F-U-N.
Oh, okay, right. Yeah, I don't know. I haven't actually looked closely at that. So there are some things known about the Ramsey properties and other convergence properties. So for example, I think, you know, if you're Ramsey and Frechet, so you need to be Frechet, I think, to make sense of this. Then I can't remember if it's alpha 3. I think the Arhangelski properties of if you have a family of sequences which converge to a single point, then you can find a single sequence which, you know, has intersection or contains mod finite or whatever. So not the weakest, but I think alpha 4 is the weakest. Maybe they're even weaker ones, but it has the alpha 3 property, I'm pretty sure. And we have a consistent example to show it doesn't have the alpha 2 property. That it may not, that it doesn't apply. And but I haven't looked at, so there are lots of convergence properties, but the other one is Frechet Eurozone for finite sets. And to be honest, I haven't yet looked at this one. And this might be a good one as well, because this Frechet Eurozone for finite sets came up in Szeptycki is the one who defined it, and she was interested in Malichin's problem about whether or not a countable, a separable topological group was necessarily metrizable or first countable, and so or Frechet rather. And so this property came up in that context. So it has some influence or some bearing on topological groups, which is kind of also what I've been thinking about, you know, one of my early, you know, ill-formed questions about applications. What's going on in topological group setting with this Ramsey property? So that might be worth looking at.
So you haven't thought about anything having like Ramsey plus Efufin?
Yeah, I don't know. I haven't thought about it. No. So it's definitely worth thinking about. Yes.
Okay, good.
I don't know if there's really anything interesting there or not, but yeah. Oh, and there's a comment from Carlos, and 2 Ramsey implies alpha 4. Okay, so just 2 Ramsey, but was I correct in saying that the full Ramsey in Frechet implies alpha 3? I think I checked that a while ago, and it didn't seem actually hard, but do you know Carlos or not? Okay, so it's also easy. Oh, he says he doesn't know. Okay, so I'm pretty sure it's alpha 3. That alpha 3 is right, but I may have to check that again to be sure. Okay, well.
Were you asking about Ramsey implies alpha 3 alone without Frechet?
Maybe you don't need Frechet. I can't remember if I need. I guess for me, these alpha I properties aren't really interesting unless you're also in a Frechet space. I know you can define them without being Frechet, but I thought Ramsey was implying alpha 3, but I might be wrong. Maybe it is only alpha 3.
In the case of almost disjoint families, that's true, and it's also easy.
Yeah,
I'm not sure in general.
I thought it was okay. I have to go back and think of that. I won't be able to. It's sort of, you try the obvious thing and it seems to work, but I have to go back and think about it again. Yeah. My point is that these things, I think the relationship between this Ramsey property and other convergence properties is interesting, and I haven't looked at the Frechet Eurozone for finite sets, and I think that's certainly worth doing.
Okay, does anyone else has a question or comment? Julian, you will interrupt me. So at the moment, do you have any question? No? Okay, well, so we thank to Paul one more time for your help and process of our invitation to this seminar for Latam.
My pleasure.
So,
Thank you.
let me stop this.